What if everything we think we know about the universe is just the tiniest fragment of a far grander, stranger truth? Picture the earliest moments of existence, a searing, unfathomable burst of energy, space stretching faster than light itself, and the very laws of physics bending in ways that still leave scientists speechless. This was the cosmic inflation era, a blink of cosmic time so brief yet so explosive that it set the stage for everything that followed. And hidden within those fleeting moments are 25 mysteries so profound, so utterly baffling, that unraveling them could rewrite the textbooks of reality. Imagine a universe younger than a trillionth of a second, already defying every rule we take for granted. Matter didn't behave like matter. Time didn't flow like time. Forces we consider unshakable were still finding their footing. It's a realm where particles blinked in and out of existence, where space itself expanded faster than a beam of light could chase it, and where the seeds of every galaxy, every star, every atom in your body were planted in a single, incomprehensible instant. Yet for all we've pieced together, this epoch guards its secrets fiercely. Why did inflation start, and why did it stop? What strange energy fueled it? And how could something so violent leave behind a universe so perfectly balanced, so finely tuned for life? These aren't just academic riddles, they're cosmic detective stories, each one a thread tugging at the fabric of reality. Somewhere in these mysteries lies the answer to why we exist at all, and that's what makes this journey so thrilling. Because every time we think we've glimpsed the truth, the universe tosses us another paradox, another enigma that refuses to fit neatly into our equations. But that's the beauty of exploration. Each question pulls us deeper into the unknown, closer to revelations that could redefine existence itself. So let's venture into those first unimaginable moments where the cosmos was wild, untamed, and whispering secrets we're only beginning to hear. What set the cosmos ablaze with that first unimaginable surge of expansion? The origin of inflation remains one of the most tantalizing puzzles in all of physics. Think of it like a match striking in the darkness, but instead of fire, the spark was a bizarre, repulsive energy that sent space itself stretching at speeds beyond light. Scientists still grapple with what could have unleashed such a force. One leading theory points to quantum fluctuations, those tiny, random ripples in the fabric of reality at the smallest scales. In the frenzy of the early universe, these microscopic wobbles might have been stretched to cosmic proportions, becoming the seeds for everything we see today. But there's another contender: scalar fields, invisible energy landscapes that could have tipped the universe into hyperdrive. Picture a ball rolling down a hill, except this hill was made of pure, unstable energy. When the ball reached the bottom, the energy released might have kick-started inflation. The wild part, these fields don't just vanish. Some theorists believe remnants of them still linger, hidden in the dark energy accelerating our universe today. What makes this mystery so gripping is how it reshapes our understanding of spacetime's birth. Inflation wasn't just expansion, it was a rewrite of the rules. For a fraction of a second, gravity itself might have acted in reverse, pushing instead of pulling. Space didn't just grow, it exploded into being, smoothing out wrinkles and setting the stage for galaxies to form billions of years later. Yet for all its elegance, inflation raises thorny questions. Why did it last just long enough to create a universe so finely balanced? Was it pure chance, or is there a deeper mechanism we haven't uncovered? Every answer we think we have only peels back another layer of the cosmic onion. One of the most baffling absences in the cosmos might hold the key to understanding inflation's aftermath: the case of the missing magnetic monopoles. These hypothetical particles are like the universe's unfinished business. Grand unified theories insist they should be everywhere, littering space like cosmic breadcrumbs from the inflationary era. Yet not a single one has ever been detected. So where did they go? Think of monopoles as the universe's mismatched socks. particles with just one magnetic pole, either north or south, unlike the paired poles we see in every magnet today. In the chaos of the early universe, when forces like electromagnetism and the strong nuclear force were still intertwined, these oddities should have formed in staggering numbers. Inflation's rapid expansion ought to have stretched their distribution across the cosmos, making them impossible to miss, but our detectors remain eerily silent. This vanishing act isn't just a curiosity, it's a crisis for physics. One possibility: inflation didn't just stretch space, it diluted monopoles to near non-existence, scattering them so thinly that finding one is like searching for a single grain of sand in a galaxy. Another twist: monopoles might be hiding in plain sight, masquerading as other particles or lurking in regions of space we haven't probed yet. Experiments like MOEDL at the Large Hadron Collider are hunting for them in high-energy collisions, while cosmic ray detectors scour the skies for monopoles raining down from space. The stakes couldn't be higher. If monopoles exist, they'd validate theories that unify all fundamental forces. If they don't, it means our best models are missing something profound. Either way, their absence whispers a tantalizing clue. That inflation didn't just shape the universe, it might have erased the very evidence of its own origins. And that's the kind of paradox that keeps physicists awake at night. The cosmos has a curious habit of looking strikingly similar in every direction, a fact that baffled scientists for decades. Take the cosmic microwave background, that ancient afterglow of the Big Bang. No matter where we point our telescopes, its temperature varies by less than 1 part in 100,000. But here's the puzzle. Regions of the universe now billions of light-years apart were once so distant that not even light could have bridged the gap between them in the time since the Big Bang. So how did they end up so perfectly in sync? This is the horizon problem, and inflation's solution seems almost too elegant. By stretching space faster than light could travel, inflation could have taken a tiny, thermally balanced speck of the early universe and blown it up to cosmic proportions, preserving that uniformity across vast distances. It's like smoothing out wrinkles in a tablecloth by yanking its edges apart, except the tablecloth is space-time itself. Yet for all its explanatory power, this answer opens a deeper rabbit hole. What existed before inflation, and why does the CMB still hold subtle anomalies that refuse to fit the tidy inflationary narrative? The Planck satellite's meticulous maps of the CMB revealed faint but stubborn irregularities, cold spots, asymmetries, and strangely aligned patterns that defy standard inflationary predictions. One particularly eerie anomaly, dubbed the axis of evil, suggests large-scale temperature fluctuations that aren't randomly distributed but oddly aligned along a particular direction in space. If inflation truly randomized everything, why do these ghostly fingerprints of order persist? Some theorists wonder if they're echoes of a pre-inflationary universe, a fleeting glimpse of whatever cosmic turbulence existed before the inflationary storm. Others propose even wilder ideas, that our universe collided with another bubble universe during inflation, leaving scars in the CMB, or that the laws of physics weren't yet settled during those first frenzied moments. The most unsettling possibility: inflation might not be the final word. Alternative theories, like bouncing cosmologies or scenarios where the speed of light was radically different in the early universe, are gaining traction. Each one challenges us to rethink not just how inflation began, but whether it began at all, or if it's merely one chapter in a far stranger cosmic story. The horizon problem was supposed to be inflation's crowning triumph. Instead, it's become a doorway to questions we're only starting to articulate, let alone answer. And that's the irony of cosmic mysteries. Every solution invites us to peer further into the dark, where the next enigma is always waiting. At the heart of cosmic inflation lies one of the greatest hypothetical entities in physics, the inflaton. This mysterious field, or its associated particle, is believed to have orchestrated the universe's exponential growth, acting like an invisible hand that stretched space-time itself. But here's the catch: despite shaping the cosmos, the inflaton remains entirely theoretical. No experiment has ever detected it, and its properties exist only in equations and simulations. So what exactly are we dealing with? Think of the inflaton as a cosmic puppet master, an energy field that temporarily rewrote the rules of gravity. Unlike familiar fields like electromagnetism, which weaken with distance, the inflaton's energy density stayed bizarrely constant as space expanded, creating a self-sustaining runaway effect. Picture blowing up a balloon while the air inside somehow never thins out. That's the inflaton's signature trick. Most theories suggest it eventually decayed, dumping its energy into the hot soup of particles we recognize as the early universe. But its fleeting existence left an eerie silence, no direct traces, just echoes in the large-scale structure of galaxies and the whispers of the cosmic microwave background. The hunt for the inflaton splits physicists into competing camps. Some models treat it as a fundamental particle, cousin to the Higgs boson but with a far more dramatic role. Others imagine it as an emergent property of multiple fields interacting in ways we don't yet grasp. Then there's the chaotic inflation scenario, where random quantum fluctuations kicked off different rates of expansion in different regions, potentially birthing a multiverse of bubble universes with their own unique physics. Each model tweaks the inflaton's behavior: how long it lasted, how abruptly it shut off, even the kinds of quantum ripples it imprinted on spacetime, the real frustration. Current technology may never spot the inflaton directly. To catch a glimpse, we'd need particle colliders with energies 1 trillion times beyond the Large Hadron Collider, machines the size of solar systems. Some researchers pin hopes on indirect signatures, like primordial gravitational waves frozen into the CMB, which could reveal how violently the inflaton shook spacetime. Others speculate that if the inflaton's remnants still permeate the cosmos, they might subtly alter how dark energy behaves billions of years from now. What makes this search so electrifying is the sheer audacity of the stakes. Proving the inflaton's existence wouldn't just solve inflation's mysteries, it would expose the hidden architecture of reality itself. Until then, it lingers as physics' ultimate ghost story, a force that shaped everything we know, then vanished without a trace. If inflation never truly stopped, if pockets of spacetime kept stretching exponentially while others stabilized, what would that mean for reality? Welcome to the multiverse conundrum, where eternal inflation doesn't just explain our universe's birth, but suggests the existence of countless others, each with its own laws of physics. Alan Guth and Andre Linde, architects of inflationary theory, proposed this dizzying possibility: that our cosmos is just one bubble in an infinite cosmic froth, forever expanding and spawning new universes. But here's the rub: if these other realms are forever beyond our observational reach, does this idea cross from science into pure speculation? The math paints a surreal picture. In eternal inflation, quantum fluctuations could spark new inflationary domains within an already expanding spacetime, like bubbles forming in a boiling pot. Each bubble becomes its own self-contained universe, with random variations in fundamental constants, some where gravity is stronger, others where atoms never form. Linde famously compared it to a growing fractal, where every branch births new realities ad infinitum. The numbers technically work, but critics like Paul Steinhardt argue this isn't science, it's a philosophical rabbit hole. If we can't observe, measure, or falsify these other universes, how is this different from metaphysics? The debate cuts to the core of what science can claim to know. Proponents counter that the multiverse isn't entirely untestable. Subtle fingerprints might linger in our own universe, anomalies in the cosmic microwave background, like bruises from collisions with neighboring bubbles, or patterns in large-scale galaxy distribution that hint at inflationary quirks. Some even suggest that dark energy's peculiar behavior could be a relic of our bubble's unique inflation history. Yet these signals are maddeningly ambiguous, leaving room for rival theories. What makes this clash so electrifying is how it forces us to redefine scientific progress. Guth and Lind see the multiverse as an inevitable consequence of inflation's math, a feature, not a bug. Their opponents warn it risks making cosmology untestable, a playground of elegant equations divorced from evidence. Meanwhile, philosophers chime in. If the multiverse is real, it might resolve the fine-tuning problem, explaining why our universe's constants seem perfectly calibrated for life. After all, in an infinite ensemble, some universes had to hit the jackpot, but there's a haunting irony here. Inflation was meant to solve mysteries, not spawn new ones. Yet the multiverse hypothesis does something remarkable. It turns the cosmos into a laboratory for the wildest thought experiments. Whether it's ultimately proven or discarded, it challenges us to ask not just how the universe works, but what science is willing to dream. And that tension between what we can prove and what we dare to imagine is where the next breakthroughs might hide. Inflation was supposed to solve one of the Big Bang's thorniest problems, the singularity, that infinitely dense, infinitely hot point where all physics breaks down. But did it really dodge the singularity or just sweep it under the cosmic rug? The math of inflation still points back to a moment where energy density becomes infinite, where space-time curvature goes haywire. It's as if we replaced the Big Bang's glaring paradox with a subtler, more sophisticated version of the same puzzle. Loop quantum cosmology offers a way out, a radical rewrite of the rules where gravity turns repulsive at ultra-high densities, preventing collapse into a singularity. Picture space-time not as smooth and continuous, but woven from tiny, indivisible loops. At the smallest scales, these loops resist further squeezing, like a cosmic mesh that rebounds rather than crushes. The result, a big bounce instead of a big bang, with our universe emerging from the collapse of a previous one. No infinities, no singularities, just an endless cycle of contraction and rebirth. Yet even this elegant idea faces hurdles. If a prior universe existed, where's the evidence? Some theorists hunt for imprints in the cosmic microwave background, subtle swirls or temperature anomalies that could betray a pre-bounce universe's final moments. Others suggest gravitational waves from the bounce might linger at frequencies too low for current detectors. The problem is stark. Without observable signatures, the bounce remains as speculative as the singularity it replaces. Meanwhile, string theory proposes its own workaround brainworld scenarios where our universe is a three-dimensional island floating in higher dimensional space. Collisions between these brains could ignite cosmic expansion without a singularity, like two sheets of paper smacking together to create a spark. But here, too, confirmation is elusive. The energy scales involved are so extreme that even next-generation particle colliders might never glimpse the extra dimensions required. What's striking is how each alternative, loops, brains, bounces, reveals the same tension. Our theories crave resolution, but the universe guards its deepest secrets fiercely. Inflation's singularity, sleight of hand, might feel unsatisfying, but until we catch a whisper from beyond the bang, it's the best story we've got. And that's the paradox at the heart of cosmology. The closer we get to time zero, the more reality resists. Inflation's greatest magic trick wasn't the explosive expansion, it was the stop. For the universe to transition from a hyperstretched void to the dense, particle-filled cosmos we know, inflation had to shut off with near impossible precision. Too soon, and the universe would collapse back on itself. Too late, and space would stretch so thin that matter could never clump into galaxies. This razor's edge balance is called the graceful exit problem, and it haunts physicists like an unsolved equation. Picture inflation as a cosmic engine running at full throttle. To avoid tearing reality apart, that engine needed an off switch, a moment when the inflaton field's energy collapsed, dumping its contents into the newborn universe. This violent release, known as reheating, was like throwing gasoline on a fire. Suddenly, space seethed with particles, antiparticles, and radiation, temperatures soaring to quadrillions of degrees. Simulations suggest it might have looked like a frothing quantum ocean, with energy condensing into matter in chaotic bursts. Yet somehow, this frenzy left behind a universe perfectly calibrated for structure. Enter hybrid inflation, an elegant twist on the original theory. Here, two fields work in tandem, one driving the expansion, the other acting as a kill switch. Think of it like a pressure valve. As the primary inflaton field stretches spacetime, a secondary field accumulates tension until it snaps, triggering inflation's abrupt end. This model sidesteps the fine-tuning nightmare by making the exit mechanism built-in, not luck-dependent. But even this solution has cracks. Some versions of hybrid inflation predict exotic relics, cosmic strings, or domain walls that we've yet to spot. Reheating's aftermath holds its own mysteries. The process should have generated gravitational waves, faint ripples in spacetime that ought to linger today. Yet our detectors hear only silence. Is the signal too faint, or did reheating unfold in ways we haven't imagined? Some theorists propose warm inflation, where energy transferred smoothly, avoiding the usual turbulence. Others wonder if dark matter particles were forged in those first fiery moments, their fingerprints hiding in the cosmic background. The deeper we dig, the clearer it becomes. Inflation's end wasn't just a transition, it was a metamorphosis. Every atom, every force, even the arrow of time might trace back to how that primordial energy decayed. Get the math wrong by a hair and stars never form. Get it right and the universe blooms. That's the haunting beauty of the graceful exit problem. It's not just about how inflation stopped, but how something so chaotic could leave behind a cosmos so improbably alive. One of inflation's most tantalizing predictions is written in the fabric of spacetime itself: primordial gravitational waves. These ripples, generated during the universe's violent expansion, should have left faint swirls in the cosmic microwave background, a telltale fingerprint called B-mode polarization. Finding it would be like uncovering the cosmic equivalent of a crime scene photo from inflation's first moments. Yet despite decades of searching, these waves remain stubbornly absent. The silence is deafening, and it's forcing physicists to confront an uncomfortable question. Did we get inflation wrong, or are we just not listening carefully enough? The hunt for B-modes is a story of soaring hopes and humbling setbacks. In 2014, the Bicep 2 team thought they'd struck gold, announcing a detection that turned out to be cosmic dust masquerading as a signal. Since then, experiments like Polar Bear and the South Pole Telescope have pushed sensitivity to unprecedented levels, filtering out galactic interference with painstaking precision. Still, the primordial waves evade capture. Theories that once seemed airtight now face scrutiny. Could inflation have been quieter than we thought, or are the waves hiding in frequency ranges beyond our current text grasp? Enter Lightbird, Japan's upcoming space-based observatory, designed to scan the CMB with clarity 10 times sharper than any predecessor. Its mission: comb through the noise for those elusive swirls, like picking out a whisper in a hurricane. But even Lightbird prowess has limits. Primordial waves from inflation would stretch across light years, their frequencies far lower than the tremors LIGO detects from colliding black holes. LIGO laser interferometers are exquisitely tuned to high-frequency ripples, the cosmic chirps of compact objects. Inflation's waves, by contrast, would be a near-static hum, requiring detectors of planetary scale or space-based arrays we've yet to build. The drought isn't just a technical challenge, it's a philosophical pivot. Some theorists argue that B-mode's absence hints at alternatives to inflation, like bouncing cosmologies or string gas scenarios. Others propose more exotic inflation models where gravitational waves were suppressed, perhaps by extra dimensions or unknown symmetries. The irony is thick. Inflation's strongest evidence was supposed to be written in gravity's language. Now, its silence might be rewriting the theory itself. What makes this search so gripping isn't just the potential discovery, it's the stakes. If B modes appear, they'll reveal inflation's energy scale, exposing whether grand unified theories are on the right track. If they don't, the cosmos might be nudging us towards something even stranger. Either way, the drought isn't empty silence. It's a question hanging in the void, waiting for the right ears to hear it. The universe has a shape, or rather, a stunning lack of one. After inflation's frenzy, space emerged with a curvature so precise it borders on mathematical perfection, zero. Not positively curved like a sphere, not negatively curved like a saddle, but flat to within 1 part in 10,000. This cosmic flatness isn't just a quirk, it's a screaming anomaly. Because without inflation's relentless stretching, even the tiniest initial curvature should have ballooned into something extreme. So why does our universe look like it was leveled by an obsessive cosmic surveyor? Imagine blowing up a balloon covered in pencil marks. As it inflates, any small bumps or dips smooth out, making the surface appear flatter and flatter. Inflation did that to space-time, stretching any initial curvature so thin it became negligible. The math works beautifully, but it leaves physicists uneasy. A perfectly flat universe requires an almost uncanny balance between the energy density of matter, radiation, dark energy, and the expansion rate itself. Tweak any one by a hair and space curves dramatically. Yet here we are in a cosmos where parallel laser beams stay parallel across billions of light years. Now for the twist. While our best measurements, cosmic microwave background data from Planck and large-scale galaxy surveys, support flatness, they don't rule out subtle curvature hiding just below detection thresholds. Some models suggest a universe so vast that its curvature is only visible on scales larger than our observable horizon. Others play with exotic ideas that dark energy's repulsive force is actively flattening space over time, or that multiple inflation phases left behind nested regions with different curvatures. To test these wild possibilities, cosmologists run universe-scale simulations, start with a slight positive curvature, and watch galaxies clump differently than in flat space. Introduce negative curvature, and voids between galaxy clusters stretch into bizarre hyperbolic labyrinths. But reality stubbornly matches the flat simulation every time. That's either a staggering coincidence or a clue that inflation's flattening effect is baked into something deeper, a fundamental symmetry we haven't cracked yet. The unsettling truth: flatness might not be fine-tuning at all. In string theory, certain higher dimensional geometries naturally unwind into flat three-dimensional universes. Quantum gravity models hint that space-time could self-correct toward flatness, like a sheet of ice smoothing under its own tension. Or perhaps flatness is an illusion, our local patch of a vast, crumpled multiverse where only the flattest regions foster life. Every explanation pushes the mystery deeper, challenging us to ask not just how the universe got its shape, but whether shape even means what we think it does. From the quantum frenzy of inflation emerged the galaxies, stars, and cosmic structure we see today. But how? The leap from microscopic quantum jitters to vast galactic superclusters is one of the most astonishing transformations in nature, like watching a subatomic whisper grow into a thunderous cosmic shout. During inflation, spacetime wasn't just stretching. It was crackling with quantum fluctuations, particles and energy popping in and out of existence in a microscopic dance. Inflation's relentless expansion stretched these quantum ripples to astronomical scales, freezing them into the very fabric of the cosmos. These imprints later became the gravitational seeds for everything regions where matter clumped slightly denser, destined to become galaxy clusters and lighter patches that evolved into vast cosmic voids. Think of it as Schrödinger's cat on a universe-sized scale. In the quantum realm, particles exist in superpositions, multiple states at once, until observation collapses them into definiteness. Similarly, inflation's quantum fluctuations were a blur of probabilities until the universe cooled enough for gravity to observe them, locking in density variations that shaped cosmic structure. This transition from quantum fuzziness to classical certainty should have erased quantum weirdness entirely. Yet galaxies bear its fingerprints, a paradox that still rattles physicists. How could delicate quantum behavior survive the violent chaos of the early universe to imprint itself so precisely? Roger Penrose offers a stark objection: quantum mechanics and gravity don't play nice. In his view, gravity's role in collapsing quantum states isn't just incidental, it's fundamental. He argues that the universe's smoothness contradicts quantum randomness, suggesting inflation's quantum-to-classical leap might be a mathematical sleight of hand. Instead, Penrose proposes conformal cyclic cosmology, where the universe's death and rebirth naturally smooth out quantum noise, avoiding the need for inflationary stretching altogether. His critique cuts deep. If quantum fluctuations were truly random, why does the large-scale universe look so orderly? The debate hinges on a cosmic Rorschach test. What some see as quantum fingerprints, others interpret as flaws in the theory. Future galaxy surveys, like those from the Vera Rubin Observatory, could settle part of the dispute by mapping the distribution of matter with unprecedented precision. If inflation's predictions hold, the patterns should align with quantum-stretched ripples. If they don't, we might need a radical rewrite of cosmology's opening chapter. The quantum-to-classical transition isn't just a technical detail, it's the moment probability crystallized into reality, setting the stage for everything that followed. And that's a mystery worth chasing to the edge of the observable universe. Could the same force that hurled the universe into existence still be lurking in the shadows today? Dark energy, the enigmatic push accelerating cosmic expansion, bears an eerie resemblance to inflation's explosive repulsive gravity. Both phenomena stretch space itself, both defy ordinary matter's gravitational pull, and both operate as mysteries wrapped in equations. The tantalizing possibility: dark energy might not be new at all. It could be inflation's dying ember, a relic of that primordial fire dimmed to a faint but persistent glow. The case for this cosmic connection starts with their shared mathematical DNA. Inflation's driving force was likely a scalar field, an invisible energy landscape that temporarily dominated the universe. When inflation ended, that field didn't just vanish, it decayed, dumping its energy into particles and radiation. But what if a sliver of it survived, lingering as a background hum? Enter quintessence, a dynamic dark energy model where a slowly evolving scalar field mimics the cosmological constant, but with a twist. Its energy density can change over time. Unlike static vacuum energy, which maintains constant repulsive force, quintessence ebbs and flows, potentially explaining why dark energy's dominance began relatively recently in cosmic history. Yet the plot thickens with competing explanations. Vacuum energy, the other leading dark energy candidate, treats empty space as anything but empty. Quantum fluctuations constantly birth particle-antiparticle pairs that annihilate in flashes of energy. Summed across the universe, this zero-point energy could generate repulsive gravity. But here's the snag: theoretical calculations overshoot observed dark energy density by a ludicrous factor of 10 to the power of 120. This worst prediction in physics suggests either a glaring error in our math or a cancellation mechanism so precise it feels like cosmic conspiracy. The debate isn't just academic. If dark energy is quintessence, future observations might catch it subtly weakening or clustering in space. Upcoming telescopes like Euclid and the Roman Space Telescope will map dark energy's influence with unprecedented precision, hunting for telltale wrinkles in galaxy distributions. If it's vacuum energy, the search turns toward quantum gravity, a theory that might finally reconcile those catastrophic calculations. What makes this mystery so electrifying is its existential stakes. If dark energy is inflation's echo, we're tracing a thread back to the universe's first moments. If it's something else entirely, we might be standing at the edge of a paradigm shift. Either way, the cosmos is whispering its secrets if we're bold enough to reinterpret what we think we know. At the crossroads of cosmology and quantum gravity, a startling paradox emerges, one that pits the holographic principle against the inflationary universe's sheer enormity. String theory suggests reality might be a cosmic mirage, with all physical information encoded on a two-dimensional boundary like a hologram. Black holes, those ultimate entropy factories, seem to obey this rule. Their maximum entropy scales with surface area, not volume. But inflation's aftermath, a universe exponentially larger than our observable patch, throws this delicate balance into chaos. If the holographic bound holds, how could the infant universe's entropy possibly fit within its projected limits? Picture black hole thermodynamics as the universe's strictest librarian. Every bit of information falling into a black hole gets stamped onto its event horizon, with entropy proportional to the horizon's area. This holographic behavior suggests a profound truth. Perhaps all spacetime is just a projection from some distant surface. Now rewind to inflation, where quantum fluctuations generated entropy on a scale that defies intuition. By stretching microscopic randomness to cosmic proportions, inflation should have produced entropy far beyond what any holographic surface could encode, like trying to cram an entire library into a single bookshelf. Leonard Susskind and Gerard T. Hooft first sounded the alarm. If the holographic principle is fundamental, then inflation's vast entropy either violates it or demands a radical rethink of how information scales in an expanding universe. One daring resolution, the causal patch hypothesis. It proposes that only the observable universe, a tiny fraction of the whole, matters for holography, effectively placing an information firewall beyond our cosmic horizon. But this feels like sweeping the problem under the rug of unobservability. Alternative ideas twist the knife deeper. Might inflation's spacetime be holographic in a way we're missing? Some string theorists suggest that higher dimensional brains could host inflationary dynamics while preserving holographic bounds, like a three-dimensional movie projected from a two-dimensional reel. Others argue that entanglement entropy, the quantum links between distant particles, could provide extra storage space for information. Then there's the nuclear option, that the holographic principle simply breaks down during inflation, revealing its limits as a description of quantum gravity. The tension here isn't just technical, it's existential. If holography can't contain inflation's chaos, does that mean we've misread reality's blueprint? Or is inflation the stress test that finally reveals where our theories fracture? As detectors like LIGO listen for gravitational waves and quantum computers simulate holographic codes, we're left staring at a cosmic Rorschach test, one where the ink blots might just rewrite the rules of space, time, and information itself. Inflation's most perplexing trick might be its ability to make the impossibly small not just visible, but universe-shaping. Quantum fluctuations tinier than the Planck length, nature's smallest possible scale, were stretched to astronomical sizes during cosmic inflation, imprinting themselves on the cosmos like fingerprints on blown glass. But here's the catch: at scales below the Planck length, roughly 10 to the power of -35 meters, our understanding of physics shatters. Gravity and quantum mechanics cease to play nice, space-time loses its smoothness, and the very concept of distance becomes meaningless. So how can inflation take phenomena from this forbidden realm and project them onto the sky without breaking reality's rules? This is the trans-Planckian problem, and it's a crack in cosmology's foundation. Picture a subatomic violin string vibrating at frequencies so high they defy measurement. Inflation plucked those strings, stretching their oscillations until they became the density variations that seeded galaxies. but according to standard physics, those ultra-high-frequency vibrations shouldn't even exist, or at least they should behave in ways our theories can't describe. It's like trying to predict the weather using only a thermometer. The tools we have aren't equipped for the job. Some theorists argue this isn't just a gap in knowledge, it's proof that inflation requires new physics to avoid internal contradictions. Enter modified dispersion relations, one of the boldest attempts to bridge this gap. In ordinary physics, a wave's frequency and wavelength are locked in a fixed relationship like a singer's pitch matching the length of their vocal cords. But near the Planck scale, this relationship might warp dramatically. Quantum gravity effects could twist spacetime into a foamy, turbulent medium where high-frequency waves slow down or scatter unpredictably. If true, this would mean inflation's quantum fluctuations weren't simply frozen. They were filtered, their highest energies dampened by the fabric of reality itself. The implications are staggering. Certain modifications to dispersion relations could leave subtle fingerprints in the cosmic microwave background, like faint asymmetries in temperature fluctuations or unexpected patterns in galaxy clustering. Experiments like the Simons Observatory are hunting for these anomalies with razor-sharp precision. Others might lurk in the gravitational wave background, where primordial ripples could carry echoes of their trans-Planckian origins. But the real shocker, some models suggest these modifications could make the universe's expansion history look radically different, almost as if inflation never happened at all. Critics counter that tweaking dispersion relations is a band-aid, not a cure. Without a full theory of quantum gravity, we're essentially guessing how physics behaves at these extreme scales. String theory offers one alternative, that trans-Planckian modes are shielded by extra dimensions, their true behavior hidden from our three-dimensional view. Loop quantum gravity proposes another, that spacetime's granular nature imposes a hard cutoff, preventing fluctuations smaller than the Planck length from existing in the first place. At its core, the trans-Planckian problem forces us to confront an uncomfortable truth. Inflation's success might be built on physics we don't yet understand. Those quantum fluctuations weren't just stretched, they were smuggled across a boundary where our equations go blind. Whether this reveals a deeper layer of reality or a fatal flaw in inflationary theory depends on what future observations uncover. Until then, it stands as a reminder that even our most elegant cosmic stories might be missing their most crucial pages. If our universe is just one bubble in a frothing multiverse sea, then collisions between inflating cosmic domains aren't just possible, they're inevitable. When two bubble universes expand and intersect, the crash should leave scars. Not scars in the familiar sense, but imprints frozen into the cosmic microwave background. Subtle temperature variations or polarization patterns that defy ordinary inflationary predictions. These bruises would be the closest thing we have to a cosmic crash scene photo, revealing not just that we collided, but when, how violently, and perhaps even what laws of physics governed our neighbor. Simulating these collisions paints a surreal picture. As two bubbles meet, their inflationary energy fields interact like storm fronts clashing in space. The boundary between them becomes a wall of concentrated energy, warping spacetime and triggering shockwaves that ripple through both universes. Depending on the energy difference between bubbles, the collision could send gravitational tsunamis rolling through ours or leave behind a disk of distorted CMB temperatures like a cosmic bullseye hovering in the sky. Some models even suggest these collisions could alter fundamental constants locally, creating regions where physics subtly shifts. The hunt for these bruises is already underway. Scientists have scanned the CMB for telltale circular anomalies, disruptions in the background radiation's uniformity that might betray ancient impacts. One candidate, the so-called cold spot, a vast, unexplained region of unusually low temperatures in the southern galactic hemisphere, has fueled speculation. Could this be the echo of a long-ago collision with another universe? The evidence is shaky. Detailed analysis suggests the cold spot might just be a statistical fluke, though its exact odds of appearing naturally remain hotly debated. Future telescopes promise sharper eyes for this cosmic forensics. The CMB-S4 project, slated for the 2030s, will map microwave background polarization with unprecedented precision, filtering out galactic dust to isolate any collision signatures. Meanwhile, theorists refine their collision simulations, exploring how bubble interactions might imprint not just on temperature, but on the large-scale distribution of galaxies or the spectrum of primordial gravitational waves. The key challenge, distinguishing a true multiverse bruise from mundane astrophysical noise, like the shadows of distant galaxy clusters or quantum fluctuations from our own inflation. What makes this search so electrifying is its audacity. If we found proof of a bubble collision, it wouldn't just confirm eternal inflation, it would open a window into realities beyond our own. We could potentially learn about their physics, their histories, even whether they harbor life. Conversely, if decades pass without a single credible signal, the multiverse hypothesis might need a radical rethink. Either outcome forces us to confront a humbling truth. Our universe might not be a solitary masterpiece, but one brushstroke in a canvas vaster than we dare imagine. And the paint is still wet. The most haunting question about cosmic inflation isn't how it worked, but why it happened at all. What flicked the switch on that runaway expansion, transforming a seething quantum foam into a universe ripe for galaxies, stars, and life? The answer lurks in the murky realm of initial conditions, where physics dances with philosophy, and even the wildest theories struggle to gain footing. Consider the Boltzmann brain paradox, a nightmarish thought experiment that turns inflation's origin into a cosmic coin toss. Named after 19th century physicist Ludwig Boltzmann, the idea suggests that in an eternal, chaotic universe, random fluctuations could spontaneously assemble fully formed conscious observers, brains floating in the void, complete with false memories of a past that never existed. If reality truly boils down to statistics, why wouldn't a lone, self-aware fluctuation be more probable than an entire ordered universe? Inflation, by this logic, might not be a fundamental process but a fantastically rare accident, a fleeting bubble of order in an otherwise disordered multiverse. The chilling implication, we might just be that statistical fluke, hallucinating a cosmic history that never was. But Sean Carroll and others fire back with a radical counter-proposal. Perhaps the universe naturally self-organizes. In Carroll's vision, the Big Bang wasn't a singular starting gun but a phase transition, like water freezing into ice, where entropy, not disorder, drives the emergence of structure. His self-organizing cosmos theory suggests that certain quantum configurations inevitably lead to inflation, making our universe not a freak accident but an inevitable outcome of deeper physical principles. It's the difference between winning the cosmic lottery and gravity simply doing what gravity does. The battle between these views isn't just academic, it reshapes how we think about reality's architecture. If Boltzmann is right, everything we see could be a mirage, with the true initial condition being pure chaos. If Carroll's camp holds the answer, then the universe might possess an innate tendency toward complexity, a hidden rulebook where inflation is less a mystery and more a cosmic inevitability. The irony, both theories crash into the same wall. We can't observe what came before. Without a time machine to witness the universe's first flicker, initial conditions remain a playground for speculation. Yet perhaps clues linger in the universe's fine-tuning. The fact that inflation's parameters were exquisitely balanced to allow galaxies, let alone minds, to ponder them hints that either we're impossibly lucky or some deeper principle was at work. For now, the enigma remains, dangling between randomness and inevitability like a cosmic tightrope, and that tension between accident and destiny might be the most profound puzzle of all. Gravity is the cosmic underdog, unimaginably weaker than the other fundamental forces. A fridge magnet effortlessly defeats Earth's entire gravitational pull, and a simple static shock outweighs the planet's tug on your body. This bizarre imbalance, known as the hierarchy problem, gnaws at physicists because it hints that something fundamental is missing from our picture of reality. An inflation, with its brief reign of repulsive gravity, might hold clues to why nature treats gravity like an afterthought. To grasp the scale of the mystery, picture the forces as siblings. The strong nuclear force, which glues protons together, is about 10 to the power of 39 times stronger than gravity at particle scales. That's like comparing a hurricane to a sigh. Such a staggering difference seems unnatural, as if gravity's feebleness requires an explanation beyond the standard model. Inflation's peculiar gravity flip, where it briefly behaved as a repulsive rather than an attractive force, suggests that gravity's rules might be more flexible than we thought. Could the same mechanism that turbocharged space's expansion also have left gravity permanently diluted? One radical solution hides in higher dimensions. String theory proposes that gravity only appears weak because it's leaking into hidden spatial dimensions beyond our perception. Imagine ants crawling on a taut bedsheet. They experience their world as two-dimensional until a marble dents the fabric, creating unseen dips where gravity might pool. If extra dimensions exist, inflation could have stretched them to scales too vast for particles to traverse, leaving gravity as the sole force able to seep through. The Large Hadron Collider has hunted for signs of these dimensions by smashing protons together, hoping to spot energy vanishing into unseen realms. So far, the dimensions remain hypothetical, but their mathematical elegance keeps theorists hooked. Supersymmetry offers another tantalizing bridge. This theory posits that every known particle has a heavier, undiscovered superpartner. These shadow particles could cancel out quantum corrections that otherwise make gravity's weakness absurdly fine-tuned. Inflation's energy scales overlap neatly with where supersymmetry should kick in, suggesting the two phenomena might be cosmic bookends, one setting the stage for the universe's expansion, the other stabilizing gravity's place in the force hierarchy. Yet after decades of searching, colliders have found no trace of superpartners, leaving the theory in limbo. The wildest twist, inflation and gravity's weakness, might both stem from the same quantum anomaly, a glitch in spacetime's code where extreme energies rewrite the rules. Some models suggest that at inflation's energies, gravity briefly unified with the other forces, only to emerge weakened when they split apart. It's as if gravity never fully recovered from the cosmic upheaval, forever lagging behind its siblings. Whether the answer lies in extra dimensions, supersymmetry, or something stranger, the hierarchy problem forces us to confront an unsettling truth. Our universe's forces aren't just randomly mismatched. Their imbalance might be a fossil, a relic of inflation's violent reordering of reality. And until we solve it, gravity's whisper will keep echoing with the secrets of the cosmic dawn. One of physics' most heated debates, whether black holes destroy information, might have an even stranger counterpart in the early universe. Just as Hawking radiation suggests black holes could evaporate, taking quantum information with them, cosmic inflation's breakneck expansion could have scrambled or erased details about the universe's initial state. This isn't just a theoretical quirk, it strikes at the heart of whether reality's history is knowable at all. The paradox hinges on a fundamental principle: quantum information should never vanish. Every particle interaction, every fluctuation, leaves a trace like a cosmic ledger that can't be erased. Black holes challenged this when Stephen Hawking showed they could thermally radiate energy, seemingly without preserving the information of what fell in. After decades of debate, physicists mostly agree that black holes don't destroy information. It's somehow encoded in their radiation or event horizons. But inflation presents a trickier puzzle. When space stretched exponentially, quantum fluctuations got locked into place, frozen into the seeds of galaxies. Yet the sheer violence of that expansion might have severed correlations between particles, effectively wiping the slate clean for any pre-inflationary history. Think of it like a cosmic shredder. Imagine two entangled particles quantumly linked so that measuring one instantly defines the other, separated faster than light during inflation. Their connection stretches until it snaps, leaving no way to reconstruct their original state. This isn't just losing a puzzle piece, it's burning the box art. Some theorists argue that inflationary phase transitions could have performed similar erasures on a universe-wide scale, leaving us with a smoothed-out cosmos where critical details are forever out of reach. The stakes here are staggering. If inflation truly discards information, it could mean we're living in a cosmic palimpsest, a universe where the original writing has been scraped away, leaving only faint, indecipherable traces. This would violate quantum mechanics unitarity, the rule that says information must always be conserved. But here's the twist: unlike black holes, inflation lacks an obvious mechanism to preserve information. No equivalent of Hawking radiation exists to carry hidden quantum fingerprints. Opposing views offer glimmers of hope. Some models suggest that while inflation dilutes information, it doesn't destroy it, that the data still exists, just stretched across scales too vast to reconstruct. Others propose that gravitational waves from inflation might encode pre-inflationary details, like a faint echo of the universe's first whisper. Future detectors capable of measuring primordial gravitational waves could test this, hunting for subtle correlations that betray inflation's information-preserving hand. The wildest possibility: inflation might not be the culprit at all. Alternative theories like bouncing cosmologies or emergent spacetime scenarios could sidestep the paradox entirely by avoiding an exponential expansion phase. But until we crack quantum gravity, a theory capable of marrying inflation's physics with black hole thermodynamics, this paradox remains a gaping hole in our cosmic story. And that's what makes it so thrilling, because whether inflation erases information or just hides it in plain sight, the answer will rewrite our understanding of reality's very foundations. In the cosmic microwave background sea of subtle temperature variations, one anomaly stands out like a glaring cosmic bruise: the cold spot. Stretching nearly 2 billion light-years across, this vast region in the constellation Eridanus is cooler than its surroundings by about 70 microkelvin. That might sound negligible, but in the ultra-precise world of cosmology, it's a screaming outlier. Could this be a scar from the universe's birth, a relic from before inflation erased most traces of its violent beginnings? Or is it just a quirk of statistics, a cosmic illusion with no deeper meaning? First, the dramatic possibilities. Some theorists propose the cold spot as evidence of a cosmic texture, a topological defect in spacetime left over from symmetry-breaking phase transitions in the early universe. Picture a frozen knot in the fabric of reality, formed when fundamental forces split apart during cosmic cooling. As inflation stretched these defects, their gravitational influence could have created underdense regions like the cold spot, where space itself holds a faint memory of that primordial tangling. It's a compelling narrative, but textures aren't the only suspects. Another exotic explanation: a collision with another bubble universe during inflation. If our cosmos brushed against a neighboring realm, the energy exchange could have left behind a telltale chill, like touching an icy windowpane in the dark. Yet skeptics counter with far simpler explanations. Galaxy surveys reveal the cold spot aligns with a vast supervoid, a region of space nearly devoid of galaxies. Supervoids naturally cool photons passing through them via the integrated Sachs-Wolf effect, where light loses energy climbing out of gravitational wells. But here's the catch: this particular void isn't quite large or empty enough to explain the cold spot's extreme temperature dip. Unless our understanding of voids is incomplete, the mismatch suggests something stranger might be at play. Then there's the pesky possibility of instrumental error. Even Planck, the gold standard of CMB telescopes, isn't immune to systematic noise. Could unresolved foreground emissions or calibration quirks be masquerading as a cosmic anomaly? The cold spot's enigma has spurred some of cosmology's most creative detective work. Researchers have run thousands of simulations, testing whether such a feature could arise randomly in a standard inflationary universe. The odds, some studies claim less than 2%. Others argue it's closer to 10, just rare enough to raise eyebrows, not slam-dunk proof. Future telescopes like the Simons Observatory aim to settle the debate by measuring the cold spot's polarization patterns. If it's truly a cosmic texture or bubble collision, the polarization signal should carry distinct swirls or asymmetries. If not, the cold spot might fade into the annals of cosmic coincidences. What makes this mystery so gripping isn't just the anomaly itself, it's what it represents. If the cold spot is a pre-inflationary fossil, it's our only window into a time before time. If it's a supervoid, it challenges our models of large-scale structure, and if it's noise, then even our most precise instruments can still lead us down rabbit holes. The cold spot refuses to surrender its secrets easily, but that's the allure of cosmic detective work. Sometimes the most tantalizing clues are the ones that keep you guessing. Stephen Hawking and James Hartle's no-boundary proposal reimagines the universe's birth in a way that sidesteps the singularity entirely, by invoking a concept so abstract it bends the mind: imaginary time. Picture the Big Bang not as an explosion from nothing, but as a smooth, geometric curve where time itself behaves like a fourth spatial dimension, rounding off the universe's origin into a closed surface without edges, like the south pole of a globe. No sharp boundaries, no violent beginnings, just a seamless quantum transition from timelessness into the cosmos we know. But how could we possibly test such an esoteric idea? Enter the James Webb Space Telescope and its unprecedented power to map the universe's large-scale topology. The no-boundary proposal's key prediction lies in the universe's overall shape. If Hartle and Hawking were right, the cosmos shouldn't just be flat. It should exhibit subtle curvature on the largest scales, a relic of those early quantum geometry fluctuations. JWST deep field observations and galaxy surveys could hunt for hints of this curvature by analyzing how light bends around cosmic voids, or whether parallel laser beams eventually converge or diverge over billions of light years. Even more tantalizing are the proposal's implications for the cosmic microwave background. Certain patterns in the CMB's polarization, swirling beam modes with specific symmetry, might betray the universe's no-boundary origin, like a fingerprint left in imaginary time. Critics argue the proposal veers into untestable metaphysics. Without a clear smoking gun signature, distinguishing no-boundary cosmology from standard inflation is like trying to hear a whisper in a hurricane. But supporters counter that quantum gravity's fingerprints might hide in gravitational waves from the earliest moments. Future detectors, like the space-based LISA Observatory, could uncover primordial waves with frequencies too low for current tech waves that might carry imprints of the universe's first quantum jitters. The real intrigue, imaginary time, isn't just mathematical sleight of hand. In Hawking's framework, it represents a phase where the universe's quantum rules dominated, allowing spacetime to tunnel into existence from nothingness. Visualizing this requires ditching everyday intuition. Imaginary time flows perpendicular to real time, creating a four-dimensional space where the Big Bang isn't a point but a surface. Wrap your mind around that, and suddenly, JWST hunt for cosmic topology feels less like astronomy and more like archaeology, digging through layers of spacetime to uncover the universe's first quantum heartbeat. Whether the no-boundary proposal withstands scrutiny or not, it forces us to confront the deepest question of all, not just how the universe began, but whether beginning even means what we think it does. And that's a mystery worth observing to the edge of reality itself. If string theory is correct, our universe might be just one of 10 to the power of 500 possible configurations. A dizzying array of mathematical landscapes where the laws of physics shift with every twist of hidden dimensions. This is the string theory landscape, and its vastness presents a crushing question. How did our particular cosmic rulebook get selected from near infinite options? The answer might lie in cosmic inflation's chaotic expansion, where random quantum fluctuations could have locked in certain vacuum states while others faded into unreachable corners of the multiverse. Picture a cosmic roulette wheel spinning at the birth of spacetime, its slots representing every possible string vacuum, each with different particle masses, force strengths, even numbers of dimensions. As inflation stretched the universe, regions with wildly different physics bubbled into existence, their properties frozen by the abrupt cooling of space. Our observable universe could be one such bubble, its physics fine-tuned by sheer statistical chance. Proponents of eternal inflation, like Leonard Susskind, argue this isn't just plausible, it's inevitable. In a multiverse where every possible vacuum exists somewhere, the real mystery isn't why we landed here, but how we could have landed anywhere else. But critics like Paul Steinhardt fire back with a damning rebuttal. If any physics is possible, then nothing is explained. The anthropic principle, the idea that we observe this universe simply because it's one of the rare configurations that allows life, feels less like science and more like a philosophical shrug. If the string landscape's selection mechanism boils down to random chance, does that render string theory untestable? Steinhardt's alternative resets the board. Perhaps the universe's laws aren't accidental at all, but dictated by an underlying mathematical uniqueness we haven't yet uncovered. The debate crystallizes around falsifiability. String landscape supporters point to potential observational hints, anomalies in the cosmic microwave background that betray collisions with other bubbles, or subtle variations in fundamental constants across vast distances. Detecting these would be a long shot, but not impossible. Skeptics counter that until such evidence emerges, the landscape is a theoretical playground where predictions are so flexible they can explain anything, and therefore nothing. Amidst the clash, a third perspective emerges: dynamical selection. Some string theorists propose that certain vacua are inherently more stable, their geometries naturally favored as the universe cools. Think of water freezing into ice while countless molecular arrangements are possible. Only a few crystalline patterns dominate because they minimize energy. If true, our universe's laws might reflect not randomness, but an underlying thermodynamic inevitability. Future colliders or quantum gravity experiments could probe these ideas by hunting for signatures of extra dimensions or supersymmetry, both key ingredients in string theory's equations. What's striking is how this abstract debate forces us to confront the nature of science itself. Is a theory valid if its predictions span all possible outcomes, or does true understanding require narrowing the possibilities to something uniquely explainable? The string landscape's vastness might feel like a cop-out, or it might be the universe's way of telling us that reality's rulebook is far stranger, far more contingent than we ever dared imagine. What if the universe didn't begin with a bang, but with a bounce? While inflation dominates cosmology's origin story, Paul Steinhardt and Neil Turok offer a radical rewrite. A cyclic universe without beginning or end, where each Big Bang is just the latest collision between multidimensional brains in an eternal cosmic dance. Picture two sheets of paper, each a three-dimensional brain floating in higher dimensional space, slowly drifting together until they smack, releasing energy so explosive it births an entire universe. Then expansion, cooling, and eventually contraction, leading to another collision billions of years later. No singularity, no fine-tuned inflation, just an endless cycle of destruction and rebirth. The appeal is immediate. Unlike inflation, which relies on a one-time, inexplicable burst of repulsive gravity, the cyclic model needs no magical on switch. Each collision naturally reignites the cosmos, with dark energy, the same force accelerating today's expansion, eventually reversing to pull everything back for the next bounce. But here's where the models clash. Inflation predicts a universe smoothed to near perfection, while cyclic cosmology allows for subtle residual wrinkles from past cycles. Look closely at the cosmic microwave background's temperature variations, and you might spot the difference if the data ever tips in favor of one over the other. Brain collisions also rewrite inflation's quantum fluctuations. Instead of stretching microscopic randomness into galactic seeds, cyclic theory suggests density variations arise from imperfections in how the brains collide, like ripples on a pond disturbed by a pebble's uneven plunge. These ripples would imprint differently on the CMB, potentially leaving telltale non-Gaussian patterns, deviations from the smooth, random fluctuations inflation predicts. So far, Planck satellite data favors inflation's Gaussian signature, but the margins are slim enough to keep the debate alive. Then there's entropy, the universe's relentless slide toward disorder. Inflation starts with a low entropy bang, a mystery in itself. Cyclic cosmology sidesteps this by proposing that entropy gets reset during each contraction, not erased, but stretched so thin across the colliding brains that the newborn universe emerges statistically fresh. Critics pounce. Entropy can't just vanish, they argue. Steinhardt counters that in higher dimensions, entropy might dissipate like ink in an expanding ocean, diluted beyond recognition. The wildest implication: if brains collide, there might be others out there, parallel universes brushing against ours in extra dimensions. Unlike inflation's untouchable bubble universes, these brains could leave scars. Hunt for gravitational waves with unusual frequency spikes or inexplicable CMB asymmetries, and you might catch a glimpse of our cosmic neighbor's last impact. Whether the cyclic model triumphs or falls, its brilliance lies in its defiance. It challenges cosmology's greatest assumptions. That time has a beginning, that fine-tuning is inevitable, that inflation is the only path to the universe we see. And in that challenge, it reminds us that the boldest ideas often emerge from asking the simplest question: what if we're not the first chapter of the story, but just the latest verse in an endless cosmic poem? One of the most chilling possibilities lurking in quantum physics isn't some distant cosmic event, it's woven into the very fabric of reality around us right now. The vacuum of space isn't truly empty, it's a simmering quantum field, and its stability hinges on a precarious balance that could shatter without warning. This is the vacuum metastability catastrophe, a scenario where the Higgs field, the same field that gives particles their mass, might not be sitting at its lowest possible energy state. Instead, we could be existing in a false vacuum, a temporary plateau in the cosmic landscape with a far deeper valley of true vacuum lurking just beyond reach. If quantum fluctuations ever nudged our universe over that edge, the resulting phase transition would rewrite the laws of physics at the speed of light, leaving no warning and no escape. Picture a marble resting on a hill inside a crater. That's our current vacuum state, stable enough for now, but not the most stable configuration possible. If the marble gets enough energy to roll over the hill, it tumbles into the true vacuum below, and there's no climbing back. When applied to the universe, this isn't just a transition, it's an existential reset button. The moment a single point in space decayed to the true vacuum, a bubble of destruction would expand outward at light speed. Within this bubble, fundamental constants like the mass of electrons or the strength of gravity could change instantly. Atoms might disintegrate, stars would unravel mid-fusion, and the very fabric of space-time could reconfigure itself. The terrifying part: we wouldn't see it coming. The bubble's boundary would move faster than any information, erasing us before we even registered the threat. Calculating the odds of this doomsday scenario is where things get surreal. Using Higgs field measurements from the Large Hadron Collider, physicists estimate our vacuum's lifetime, and the numbers are equal parts comforting and eerie. Current data suggests the universe could persist for 10 to the power of 100 years before random quantum fluctuations trigger decay. That's a number so vast it dwarfs the age of the universe countless times over. But here's the catch: probabilities aren't certainties. A single quantum event could theoretically spark decay tomorrow. It's like playing cosmic Russian roulette with a gun that has a trillion chambers, statistically safe but never truly safe. The Higgs field isn't the only culprit. Some theories suggest that inflation itself might have been triggered by a previous vacuum decay in a parent universe. If that's true, our cosmic bubble could be just one in a chain of universes doomed to repeat the cycle. Certain models of supersymmetry or extra dimensions even predict lower energy vacuum states than the standard model allows, shortening our projected lifespan dramatically. Yet there's a twist that turns this existential threat into a cosmic tightrope act. If the Higgs mass were just a few % lighter, the vacuum would be completely unstable and we wouldn't be here to ponder it. If it were slightly heavier, the threat would vanish entirely. That fine-tuning raises unnerving questions. Did blind luck place us in this precarious balance, or does the universe somehow know to avoid self-destruction long enough for life to emerge? For now, the vacuum metastability threat remains suspended between theory and paranoia, a reminder that reality's foundations might be more fragile than they appear. And while the timescales involved make it a non-issue for daily life, its very possibility forces us to confront a humbling truth. The universe isn't obligated to be stable or permanent or even survivable. It just happens to be for now. Before inflation rewrote the cosmic rulebook, before time as we know it even existed, the universe was a seething quantum foam, an unfathomably dense, chaotic froth where spacetime itself flickered in and out of existence. This was the Planck epoch, a realm so extreme that even the word moment loses meaning. Durations shorter than 10 to the power of -43 seconds, distances smaller than 10 to the power of -35 meters. Here, gravity wasn't just a force, it was a wild, untamed quantum entity, warping reality into shapes beyond comprehension. To peer into this abyss, we need theories that dare to dismantle our most basic assumptions about time, space, and causality. Loop quantum gravity (LQG) offers one startling vision. Imagine spacetime not as a smooth continuum, but as a shimmering fabric woven from tiny, indivisible loops. At Planck scales, these loops knot and twist, creating a dynamic lattice where before and after blur. In this view, the Big Bang wasn't a singular explosion but a quantum bounce, a rebound from a previous universe's collapse. Picture a wave crashing onto shore, then surging back, the universe's death and rebirth in an endless cycle. LQG's equations suggest that as you rewind time, gravity eventually turns repulsive, preventing collapse into infinite density. Instead of a singularity, you'd encounter a quantum foam so dense that spacetime resembles a stormy ocean, with virtual black holes bubbling up and vanishing in a frenzied dance. Now shift to Roger Penrose's conformal cyclic cosmology (CCC), where the Planck epoch isn't a beginning but a bridge between cosmic eras. Penrose posits that as our universe expands into oblivion, all matter eventually evaporates into radiation, and spacetime becomes featureless, a state mathematically identical to the Big Bang's primordial simplicity. In this eerie symmetry, the end of one universe becomes the start of another, with information encoded in gravitational waves threading the transition like cosmic DNA. CCC's most provocative clue: rings of slightly warmer spots in the cosmic microwave background, which Penrose interprets as echoes of black hole collisions from a previous eon. Visualizing these theories requires bending animation to its limits. Quantum foam wouldn't look like foam at all, more like a hyperactive kaleidoscope where dimensions flicker, merge, and split apart. Time wouldn't flow, it would stutter, with causality loops twisting back on themselves. In LQG simulations, the bounce resembles space-time stretching like taffy until quantum pressure snaps it back. CCC's transitions play like a film running backward and forward simultaneously, with galaxies dissolving into light, then recondensing into new structures. These aren't just artistic flourishes, they're glimpses into regimes where here and now dissolve into quantum probability. Yet the Planck epoch resists even these bold frameworks. Some quantum gravity models suggest that below Planck scales, space-time might not exist at all, just a network of abstract relationships, a cosmic blockchain where geometry emerges from information exchange. Others propose that time itself is an illusion, a byproduct of entanglement between quantum subsystems. The common thread, however you slice it, the universe's first instant wasn't an event. It was a phase change, a quantum leap from no thing to something with no clock to measure it. The real shocker, these aren't pure thought experiments. Gravitational wave astronomy and ultra-precise CMB measurements might one day spot relics from the Planck epoch, anomalies in the polarization of ancient light, or high-frequency gravitational waves from quantum spacetime fluctuations. Until then, the time before inflation remains the ultimate cold case, a crime scene where the laws of physics were both the victim and the perpetrator, leaving clues written in a language we're still learning to read. And that's the paradox of studying origins. The closer we get to time zero, the more reality insists we're asking the wrong questions altogether. What if our entire universe isn't the first chapter of existence but the aftermath of a cosmic disaster? The black hole universe hypothesis turns cosmology on its head by suggesting that inflation didn't emerge from nothingness, but from the unfathomable depths of a parent universe's dying black hole. Picture this: a supermassive black hole in some primordial cosmos collapses, but instead of forming a traditional singularity, its crushing gravitational energies trigger a phase transition, spawning an entirely new spacetime bubble with its own laws of physics. Our Big Bang wasn't a beginning at all, but a rebirth from stellar ashes. This idea gains traction when you examine the eerie similarities between black hole physics and cosmic inflation. Both involve extreme curvature of spacetime. Both feature regions forever cut off from observation, event horizons versus our cosmic horizon. And both radiate energy in unexpected ways, hawking radiation from black holes mirroring the quantum fluctuations stretched by inflation. The math gets wilder when you map conformal diagrams, those stretched representations of spacetime that let physicists compare infinite scales. In these diagrams, a black hole's interior can be conformally rescaled to resemble an expanding universe, with the singularity replaced by an inflationary epoch. It's as if the universe knows how to repurpose its own catastrophic failures into fresh beginnings. The hypothesis offers elegant solutions to persistent puzzles. Why was the early universe so perfectly smooth? Because it inherited thermal equilibrium from the black hole's scrambled contents. Where did all the entropy go? It's encoded on the hidden surface of our natal black hole's event horizon, now stretched beyond our observational reach. Even dark energy finds potential explanation as residual tidal forces from the parent black hole's gravitational imprint. But the theory isn't without critics. Some argue that black hole interiors lack the right conditions to spawn inflation's repulsive gravity, while others question whether information preservation across such transitions is mathematically consistent. Then there's the elephant in the room. If we're inside a black hole, where's the singularity we're presumably falling toward? Proponents suggest it may have been erased or transformed during the bounce, converted into inflationary energy through mechanisms we don't yet understand. The most mind-bending implication: if black holes birth universes, then every time a star collapses in our cosmos, it might be igniting an entirely new spacetime. Our universe could be one layer in an infinite fractal of nested realities, each with slightly tweaked physical constants, each potentially giving rise to others. Future tests might look for subtle anisotropies in the cosmic microwave background, patterns that could betray our universe's asymmetric origin in a spinning black hole. Or perhaps gravitational wave observatories will catch echoes of pre-bang events encoded in primordial ripples. Whether the black hole universe hypothesis holds up or not, its power lies in its audacity. It dissolves the boundary between destruction and creation, suggesting that every cosmic ending carries the seeds of a new beginning. And that changes everything because if true, we're not just living in a universe. We're living inside the spectacular aftermath of a celestial phoenix. What if the absurdly precise fine-tuning of cosmic inflation isn't just luck, but evidence we're living inside an artificial construct? The simulation argument, popularized by philosopher Nick Bostrom, takes on a chilling new dimension when applied to the universe's first moments. Consider the cosmic microwave background's near-perfect uniformity. Its temperature variations fine-tuned to 1 part in 100,000, a precision so exact it mirrors the pixelated perfection of a rendered video game environment. Could the CMB be the universe's underlying code, its subtle anisotropies not quantum noise but intentional design choices? Bostrom's trilemma presents 3 stark options. Either almost all civilizations like ours go extinct before reaching technological maturity, almost none care to run ancestor simulations, or we're almost certainly living in a simulation. Inflation's razor-thin parameters where a fractionally stronger or weaker expansion would leave the universe either a collapsed lump or a lifeless void, lean unsettlingly toward the third option. Think of it like encountering a locked safe with a billion-digit combination. If someone opens it on the first try, you wouldn't assume chance, you'd suspect rigging. The universe's constants, from the strength of gravity to the mass of electrons, exhibit that same improbable precision. But here's where cosmic forensics gets fascinating. If our reality is simulated, there might be glitches in the matrix hidden in the CMB. Just as computer processors round off decimal places to save memory, a simulated universe might compress physics at extreme scales. Some theorists suggest hunting for repeating patterns in the CMB's temperature fluctuations, like a texture repeating in a video game when the system cuts corners. Others propose that high-energy particle collisions might expose the simulation's frame rate, revealing discrete spacetime steps if energy conservation breaks down at ultra-fine scales. Critics counter that invoking simulation is a philosophical dead end, an unfalsifiable claim that explains everything and nothing. Why wouldn't the simulators themselves be products of a deeper reality? And if the universe's fine-tuning seems suspicious, perhaps we simply lack the deeper theory that makes it inevitable. After all, a fish might consider water's perfect transparency, designed until it learns about refraction. The debate crystallizes around one electrifying question: is the simulation hypothesis pseudoscience or the ultimate extension of the scientific method? Future CMB telescopes could tip the scales. If they uncover pixel-like structures or mathematical signatures in primordial gravitational waves, patterns that mirror error correction codes in computer systems, even skeptics might pause. Until then, the argument remains a mirror reflecting our own limitations. Whether we're in a simulation or not, the deeper truth is this: reality, at its core, is far stranger than we've dared to imagine. These 25 mysteries, stretching from the quantum foam of the Planck epoch to the vast cosmic web of galaxies, aren't isolated riddles. They're threads in the same tapestry, each tug revealing another hidden connection. The origin of inflation ties to the missing magnetic monopoles. The trans-Planckian problem whispers to the holographic bound. Dark energy might be inflation's dying echo, while bubble universe collisions could lurk in the cold spot's chill. Even the simulation hypothesis and black hole universe scenario, as wild as they sound, force us to question whether we're seeing reality or just its shadow. This isn't just cosmology's greatest puzzle, it's a detective story where every clue rewrites the narrative. and the next chapters are being written now. The CMB-S4 experiment, with its razor-sharp sensitivity, will scan the cosmic microwave background for inflationary gravitational waves or anomalies that could betray collisions with other universes. The Einstein telescope, a next-generation gravitational wave observatory, might catch whispers from the Planck epoch itself, ripples in space-time from the universe's first quantum tremors. Even quantum computers are joining the hunt, simulating conditions so extreme they dwarf anything achievable in particle colliders. Yet for all our tools, the deeper truth remains tantalizingly out of reach. Every answer peels back another layer, revealing questions we didn't know to ask. Are we decoding the universe's true nature, or just the echoes of something grander? The cosmic inflation era didn't just birth galaxies, it left us with a cosmic cipher, written in the language of quantum fluctuations, gravitational waves, and hidden dimensions. And that's the real magic of this mystery, not just the thrill of solving it, but the awe of standing at the edge of the unknown, knowing the universe is still holding its most breathtaking secrets close. So keep looking up, because the next great revelation might not come from a telescope's lens or a supercollider's crash, but from someone bold enough to ask the next impossible question.